All right, welcome everyone. Today is going to be our, well, at least the first of two exam reviews where we go over this exam 2A from spring of 2018. So we're probably not going to be able to finish this entire exam in 50 minutes. Otherwise, it'd be a very short exam because you get 90 minutes according to this. So, but whatever we don't finish, I'll make a video on tomorrow and I'll post that as soon as I can so you guys can look at that. All right. Anyways, let's go ahead and get started. Let's see here. All right, let's begin with the multiple choice questions here. All right, so suppose that f of xy is e to the x squared minus y squared. Which of the following vectors is the direction in which f increases most rapidly at the point 1, 0? Okay, what vector gives us the direction of fastest increase? It's going to be the gradient, right? If you were here a few minutes before, we were just talking about a very similar question to that. So all we need to do is find the gradient of this and see what direction that's pointing, and we pick a vector that would be a positive multiple of that. So the gradient of f is going to be, let's see, if we do our x derivative here, we have 2x e to the x squared minus y squared. And if we do our y derivative, we have negative 2y e to the x squared minus y squared. All right, our gradient at that particular point, 1, 0, let's see what that will be. If I plug 1 into here, I have 2, and then I have e to the 1 minus 0. So I'm just going to get 2e for that. And then over here, it looks like I'm just going to get 0. Okay, so now notice that none of these actually match the answer right here. So which one am I supposed to pick? Remember, it just says in the direction. So as long as we're in the same direction, we're okay. So which one of these vectors is in the same direction as the one I just got? Yeah, that's right. It's going to end up being A right here. So there we go. So that's where we're going to increase most rapidly. All right, that wasn't too bad. Let's move on to our next one here. Calculate dz dy at the point pi 1, 0 if xyz plus sine of 2xy is 0. All right, now we could solve this for z. I guess that wouldn't be too bad for this one. But notice that z is mixed into our formula here. So that means we should probably use this formula for the z derivative, or the derivative with respect to y. It's going to be negative fy over fz, where all of this stuff combined is f of x, y, z. All right, well, let's see. Why don't we take the y derivative of this? So let's see. The y derivative will be xz plus 2x cosine of 2xy if we use the chain rule here. All right, and then what's our derivative with respect to z? That's going to give us xy, and then there actually aren't any z's in here, so it's just going to be xy. Let's see, it seems like we have an x in all of the terms, so let's cancel all of those out. And then we're going to plug in the point pi 1, 0. So partial z, partial y at the point pi 1, 0 will end up being negative z, so 0, plus 2 cosine of x times y. So that'll be 2 cosine of 2 pi, so that'll just be 2. And then we divide by 1 right here. So we end up getting negative 2 for this. But you also use implicit differentiation with respect to y. You could do that. That would almost certainly take longer. If you have a formula given implicitly with z mixed in, I strongly recommend that you do this, but it wouldn't have been wrong to do it that way, Michael. All right, so we got negative 2 for this one. All right, oh boy, we got one of these. We got one of these piecewise guys, so wise guys. But anyways, yeah, it's probably going to give us some trouble, and it's probably going to ask us something about continuity here. So let's see, which of the following statements are true? So it looks like we could have some, or maybe all of them or none of them being true. So let's see here. The first one is saying that the limit as x and y approaches 0, 0 of this is going to be 0. All right, well, what I'm going to do is I'm going to check a few different paths. And if I start to see that most of them are giving me the same number, then maybe I'll try to do something like polar coordinates or something like that to give me my specific limit. So I'm just going to try a basic path here. My first path will be y equals 0. So in that case, we're going to have the limit as x goes to 0, and then I plug in y equals 0 for all of this, and I have 0 over x squared, which is 0. All right, well, we get 0 for one of them. Now, how about we try y equals x? That's usually a pretty good one to try. So I'm going to do the limit as x goes to 0. Now, every time I see a y, I'm going to replace it with an x. So up here, I have an x squared. I already had an x squared there, and this will turn into an x squared. Okay, but all of these will cancel out, and we have the limit as x goes to 0 of 1/2, which is 1/2. And unless we want a degenerate mathematical system, 1/2 is not equal to 0 here. So that means that our limit will not agree from all possible paths, meaning that the limit will not exist. So this one is going to be false right here. Let's see, do we have to do traces or can we convert to R? You mean do different paths? I would do different paths if you suspect that it might not exist. So I just tried a few paths, but if you try a few paths, you start getting the same number every time, then convert to polar coordinates. All right, so our next statement is f is continuous at 0, 0. What do you guys think about that? You think this is a continuous function at 0, 0? Yeah, false, right? So that's going to be false because remember, a continuous function has its limit agree with the value at 0, 0. So the value of this function is 0 at 0, 0, but we don't have a limit that exists there. So there's no way it can be continuous. And if it's not continuous, can it be differentiable? Is it going to be differentiable? Yeah, no way. So it turns out that none of these statements are going to be true. So this is one of the rare occasions where we actually do have none of the above as the correct answer for one of these things. All right, so there we go. So what are the conditions for continuity? We need the value of our function, which is 0, to agree with the limit of our function as we approach 0. So if this statement was true, if P was true, then Q would have been true as well, because the limit as we approach there would have agreed with the actual value. So if this part were true, then we would have been continuous here. The polar coordinates guarantee what the limit is. They're pretty useful if x and y are approaching 0, 0. If they're approaching something else, it might be kind of hard to use them. In fact, I think we have one later on where we have to evaluate a limit that's not going to 0, 0. So we really can't use polar coordinates for that, at least not easily. All right, let's move on to our next one here. Find the equation of the tangent plane to the surface x cubed plus y cubed plus z cubed is 10 at the point 1, 1, 2. Oh, if f is continuous, how would you determine differentiability? Well, if you could find a tangent plane there, that would certainly work. Or if you have continuous x and y partial derivatives at that point, that would also guarantee differentiability. All right, so anyways, let's find our tangent plane here. So the equation of our tangent plane, if this is f of x, y, z, is partial f partial x times x minus a, partial f partial y times y minus b, and then partial f partial z, this is a y, with z minus c, and all that's going to equal 0 right here. All right, well, let's see here. So what's our x derivative? Well, we have 3x squared. But the thing is we're doing this at the point 1, 1, 2. Here, I'm going to write my derivatives over here. I'm going to do the gradient of f over here. So I have 3x squared for that, 3y squared for this, and then 3z squared here. Okay, so then when I go ahead and I plug my specific point into here, what am I going to get? Well, I'm going to have 3 because I square 1, and then I have x minus 1. And then with my y derivative, I'm also going to get 3. And we have y minus 1. And then here for my z derivative, when I plug 2 into that, I'm actually going to get 12. And then we have z minus 2 right here. All right. So let's see. Now I'm going to divide everything by 3. And then I'm going to multiply this out here. So we have x plus y plus 4z. And then we have -1, and 4 times -2 gives us -10. And then if we were to move the 10 over here, then we would get this answer here. So it looks like we're going to have an A right there. Where did the 12 come from? It came from our partial derivative with respect to z, and then we plugged in 2 into there. All right, so there we go. So we found our equation of a tangent plane, and it's by looking at the gradient of our function if all the variables are moved onto the same side. All right. Wow, we're making pretty quick work of this, actually. Number 5, if f of x is the natural log of 8 minus x squared minus 2y squared, which of the following is /r correct? The domain of f is x squared plus 2y squared is greater than 8. What do you guys think about that? Is it true or, yeah, false? Yeah, why is it going to be false? Oh, it should be less than. Yeah, because if this stuff is bigger than 8, then we're subtracting a number that's bigger than 8 right here. So let's say this stuff is maybe 9. We would do 8 minus 9, and we would have log of a natural number. So while this is false, the real domain would be this. That would be true, but since that's not what they say, that's going to be false. All right, the range of f is ln of 8 to infinity. All right, what do you guys think about that one? Is that going to be true? Yeah, this is another one that's pretty much backwards from the way that it should be. So if this were instead negative infinity to ln of 8, including ln of 8, then that would have been true because we can get any number inside here that's 8 or smaller, right? And the closer your input inside your log gets to 0, the more negative it's going to be. So you can shoot all the way down as far negative as you want if you're willing to get really close to 0. So this will hit anything from negative infinity to ln of 8, but it can't go above ln of 8 because we can't have anything positive from this stuff here. So that's false. Yeah, so you can, at this point, you could use your test logic to see that C is going to be the answer here. But let's see why this is really going to be true. The level curves of f are ellipses. Well, a level curve is where the curve where your function is going to be the same value all along the curve. So let's say that value is k. So we have k is ln of 8 minus x squared minus 2y squared. Well, let's see here. What I could do is I can exponentiate both sides. So we have e to the k is 8 minus x squared minus 2y squared. And then what I could do is I can add both of these over here and subtract e to the k over here, giving me x squared plus 2y squared is 8 minus e to the k. Now forget about how weird this looks right here. What is this? This is just some number, right? And we have x squared plus a multiple of x squared plus a multiple of y squared is some fixed number because k is a constant. So that means we're going to end up having an ellipse. So long as k is ln of 8 or smaller, which it definitely will be in this domain. All right. How do we know curvature is constant? Well, we're not really computing curvature here. A level curve is the curve where your function's the same value all along the curve. So for example, maybe, I don't know if this is exactly what it looks like, but maybe your f of xy is 1 here, and then it's 2 here, and then it's 3 along here. That's what we're doing right here. So those are the level curves. And the value for each of these, instead of being specifically 1, 2, or 3, it's just going to be k right here. Why is an ellipse based on the constant being 8 minus e to the k? It's not based on this constant at all. This could be any kind of weird constant, whatever you want it to look like. It's more that we have a number times x squared plus a number times y squared is equal to a fixed number right here. Oh, you thought this was kappa. Oh, yeah, I'm sorry. This is a k. Yeah, for the little lower leg of my k's connect to the upper leg. Kappa I'll write like this, where it kind of splits out from the k. So that's kappa. What if you plug in x and y largest possible value and you get ln of 8? Wait. Oh, okay. All right. That wasn't a question. You're answering someone's question. All right. So there we go. So I think we went over these guys right here. All right. So let's move on to number 6 here. Number 6 wants us to find these partial derivatives and then add them together. All right. Well, what's fx going to be? Well, in this case, x is our variable and y is a constant. So we have a variable raised to a constant power. How do we do the derivative of that? It's just going to be the power rule. So we lower the power, we bring the power down, and we lower the power by 1. So we have 2y times x to the 2y minus 1. So kind of like how x cubed would become 3x squared, we just bring down the old power and then lower it by 1. All right, well, what's fy going to be? Well, here, it looks like we have x squared raised to the y power, right? And in this problem, x squared is a constant. So if we ever have a constant raised to a variable power, then the derivative of that is going to be log of whatever this is times your original thing. So kind of like how the derivative of, say, 2 to the x is ln of 2 times 2 to the x, the derivative of x squared raised to the y with respect to y will be ln of my base, which is x squared, and then times x to the 2y right here. All right, so then now we just need to plug in specific numbers and add these together. So fx of e2 plus fy of e2. Let's see here. I plug in this for x, plug this in for y, so I have 4e cubed. I do that. And then here, what are we going to have here? Ln of e squared, that's going to be 2. And then we have e to the 4. So we have 4e cubed plus 2e to the 4. It also works if we treat it as 2y, right? Yeah, in that case, you would have to do the chain rule when you differentiate, but yeah, that's right. All right, is that, hopefully this is one of the answers. Is this one of the answers? Yeah, it is. All right, so there we go. So we kind of had to think about ln of e squared is just an ln thing that we know. Well, the way you do natural log of something is you imagine, okay, what power do I raise e to get what's inside? So what power do I raise e to get e squared? It's 2. So that's how we know that that was going to be 2. All right, let's go on to number 7 here. Number 7. Let f of x, y, z be x cubed plus yz squared, where x is u plus v, y is u squared minus v squared, and z is u times v. Find the derivative of f with respect to u at this particular point. All right, well, let's invoke the chain rule here. So we're going to do the derivative with respect to x. and then the x derivative with respect to u. We're going to do the same thing with y, and then we're going to do the same thing with z. All right, so we got that. So now let's actually go ahead and compute all of these. So let's see, partial f partial x is 3x squared. Partial x partial u is 1. Okay, we got that part. Partial f partial y is z squared. Partial y partial u is 2u. And then finally, when I do this, I have partial f partial z is 2yz. And then partial z partial u is v. All right. So let's see here. Now we need to know what this is at u equals 1 and v equals 1. So we won't have a problem plugging in 1 for here and 1 for there. But how are we going to get the other variables, x, y, and z? Well, fortunately, we know what those are in terms of u and v. So if I plug u and v as 1 here, we have x is 2. If I do 1 squared minus 1 squared, I get y is 0. And if I do 1 times 1, I get z is 1. So that's how we figure out what numbers those are specifically. All right, so we have 3x squared, so 3 2 squared, so it's going to be 12. Let's see, we're going to have 1 times 2 times 1, so that's 2. And then we have a y here, which is 0, so that'll all be 0. So we end up getting 14 for this one right here. All right, so that was a chain rule. So remember, if you're confused where this chain rule comes from, don't forget to draw one of these little diagrams. So f depends on x, y, and z, right? There are x, y, and z in all of these right here. So f can depend on any of those, and each one of these depends on u and v. So we have this, and we have this. Looks like I'm drawing like a magical symbol or something like that. But anyways, what we do is we follow all of the possible paths from f to u. So we can go from f to x to u, from f to y to u, and from f to z to u. And that's going to give us all of these different partial derivatives right here. I did say invoke the chain rule in the beginning. I guess that's kind of a magical word. Anyways, let's go ahead and go on to number 8 here. So use differentials to estimate the amount of metal in a closed cylindrical can with diameter 10 centimeters, AKA radius 5 centimeters. That's really what we're going to use. And a height 15 centimeters if the metal is 0.1 centimeters thick. All right, so this is going to be our, this is going to be a problem that involves differentials. So dV is going to be partial V partial R, and then dr. And then we have partial V partial H, dH. Okay, well, let's see. So this is a cylindrical can, right? So our volume for this will be pi r squared H. All right, so partial V partial R is going to be 2 pi RH, and partial V partial H will be pi r squared. All right, so we can plug these in here. 2 pi RH dr plus pi r squared dH right here. All right, so then let's go ahead and plug in every number we have here. So we have 2 pi, the radius is 5, the height is 15, and dr, well, the change in our radius is at most 0.1 centimeters, because that's how thick this is going to be. All right, now if we go over here, we have pi, we have r squared, which is 25. And then what am I going to put for dH? So they emphasize that this was a closed cylindrical can. How do you think that's going to impact what we have here? Yeah, that's right. So we're going to double it because it could have the thickness of the metal at the bottom, and it'll have the thickness of the metal at the top as well. And each one of those will be 0.1. So we have 0.2 right here. All right, and then let's compute what all of this is. 2 times 5 is 10, but then times 0.1 will cancel out. So we have 15 pi, and then 0.2 times 25 is 5. So all in all, this ends up being 20 pi. All right, wonderful. Will the volume of the cylinder be given to us? No, it will not. Yeah, you should know the volume of the cylinder and probably the volume of the cone or a cube as well. All right. So find the absolute extrema of this function right here. So we have 2x squared y, 2y cubed plus 3y squared. On the disk, x squared plus y squared is less than or equal to 1, given that f has 2 critical points with these values. All right, so they were kind enough to do part of the problem for us. They already did the part where they found the gradient and set it equal to 0. And when they did that, they ended up getting these 2 points. So we actually don't need to worry about that. So we could just write those down in our list already. So we have 0, 0, and we know that's going to be 0. And then we have 0, -1, and we know that's going to be 1. Now, all we have to do then is we have to find out any possible points on the boundary here. So we need to do that. So let's see here. What I'm going to do is I'm going to take this function and I'm going to factor out a y, because y seems to go into all of these. Okay. Now, when we're on the boundary of this is going to be the unit circle. Right? So we're looking at stuff on the boundary. Now, that's a really useful piece of information here because x squared plus y squared appears right here. So that means that this is going to be y times 2 plus 3y on the boundary. Because x squared plus y squared, anytime we see those added together, that's going to be 1, as long as we're on the boundary. All right, so that means that this is my function on the boundary right here, and it only depends on y. So remember, I want to find the maximum and minima on the boundary, and I have a function of one variable. So that means we just return to Calc 1, and we find the extreme values with this function. And now what are the limits on y? Well, since we're on the unit circle, y is going to be anywhere from -1 to 1. So we need to include those on our list as well. So if x is 0, y is -1. Oh, we already have that point. Well, then if we include this bound right here, we have 0 and then 1. And what will that be if we plug it in here? It's going to be 5. Okay, so this one's been knocked out from being an absolute anything right here. All right. How do you do it if you didn't see one of those weird identities? Well, they did give this to you. So they did give you x squared plus y squared is 1. If you wanted to, you could have done this problem with Lagrange multipliers. I haven't done this problem with Lagrange multipliers, so I have no idea how bad that's going to be. But you could try it that way if you don't want to try substituting this into your function right here. What's easiest? Yeah, I would have to do Lagrange multipliers to find out. I just picked this one because I knew I could simplify this and factor y out, and then I saw this guy. That's what made me want to substitute for this one. All right. Yeah, what's up? Yeah, sure. So we have 2x squared plus 2y squared here, right? And if we're on the boundary, x squared plus y squared is 1. That means that 2x squared plus 2y squared is 2. So all that just turned into a 2. Yeah. All right.
Hi, quick question. How did you know that y had to be in between -1 and +1? Like, how do you know that y?
Unit circle. So this domain is the unit circle, right? So the lowest possible y value we can have is -1, and the highest one we can have is 1. So that's how I knew to limit y to those values. All right. So now that we have this, we have our limitations here, and we already included these on the list. We have y is -1 and 1 on here. So we dealt with the boundary points. Now we just need to see if we take the derivative of this and set equal to 0, if there's anything like that. So f prime on the boundary will be 2 plus 6y. Well, there's no way that this is going to be undefined. Well, where did the 0, -1 come from? Well, when y is -1, if we're on the circle, our x has to be 0 right here. And we know we're on the unit circle because they gave us this right here. That's where 0, -1 came from. Oh, yeah, they also gave it to us in the problem. That's true. And 0, 1 came from the same reasoning up here. Yeah, 0, 1 up here is because we're on the unit circle, so we have to have an x value of 0 when we have y is 1. All right. So let's see here. We have f prime, and we have 2 plus 6y. We'll see where that's 0. We're going to have 6y is -2, or y is -1/3. Okay, so this is certainly a point we should investigate, y being -1/3. Okay, but how do we get the x value for this? Well, remember, we're going to be on the circle, right? Everything that we're doing in this problem is on the boundary because they already took care of the interior for us up here. So we need to plug this into the unit circle equation to see what x is. So x squared plus -1/3 squared is 1. So x squared is 8/9. So x, so we actually get plus or minus the square root of 8/3. So this actually provides us with 2 points to check. So we have root 8/3. And I didn't make my chart big enough. We have negative root 8/3 and -1/3. So these were just plus or minus for these two. Okay, now they'll actually provide, since they both have a y value of -1/3, they'll both actually give us the same value here. So we take this y as -1/3, we plug it into here to see what f is going to be. And what do we get? Well, we have 1/3 times 3 is 1. Plus 2 is going to be 3, and then times y is going to be, oh, sorry, this was -1/3, whoops. So we have -1/3 times 3 is -1, plus 2 is 1, and then times y gives us -1/3. All right, so now we've exhausted all possible options. We've got the interior points because they were kind enough to give that to us. And we got the boundary points because we just did all of this work. We found the extreme values for this function. We got -1 and 1 here. And then we took the derivative, set it equal to 0, and got a few other points as well. So now what we do is we have a big competition to see which one of these is biggest and which one's smallest. And it looks like this one's going to be our biggest. And then we have a two-way tie for smallest. So it looks like we're going to have B for this one. The maximum possible value is 5, and the minimum value is -1/3. What about 1, 0, and -1, 0 as points? Well, those didn't really show up as critical points, and they also weren't extreme values on here either. So it really wasn't required that we check those. Where did the y times 2 plus 3y come from? That came from x squared plus y squared being 1, because we were on the circle. When does the second derivative come into play? That's if we want to know local mins and maxes. But in this case, we're concerned about finding absolute mins and maxes. All right, so there's this one here. That was a good practice with extrema here. All right. So let's see here. Let f equals xy plus z squared and g be x squared plus y squared plus z squared. Find an equation, oops.
In the top.
Down, there we go. Find an equation of the tangent line at 1, 0, 1 to the curve of intersection of f equals 1 and g equals 2. All right, so we have these two surfaces rather, and they're intersecting. And we want to find the tangent line to the curve of intersection. So does anyone remember how we did this? We did this in class before. Yeah, we're going to cross the gradients. That's right. So we're going to do the gradient of f crossed with the gradient of g. That's right. Well, I guess these are uppercase, but you get what I mean. All right. So the gradient of f is, let's see, we have y. The y derivative will be x, and then the z derivative will be 2z. Meanwhile, the gradient of g, oh, well, that's pretty easy. It's just going to be 2 times each of the variables. Okay, because this is going to be some kind of sphere. Each of its level surfaces will be a sphere. All right, so now we could cross them as is, but it's going to be easier. It's going to be easier to just plug in the point right now. So let's see. If I plug in 1, 0, 1 into here, I have 0, 1, and 2. So this is at the point 1, 0, 1. And then the gradient of g here will be 2, 0, 2, right here. I set up a second order differential equation. Yeah, that's not in this class. So don't worry about doing that here. Anyways, so let's cross these. Zero, 1, 2, 2, 0, 2. All right, let's dust off our old cross product skills here. All right, we have 1 times 2 minus 0, so it's 2. For j, we have 0 times 2 minus 2 times 2 is negative 4, but j is negative, so we have positive 4. And then with k, we have 0 times 0 minus 1 times 2. So we have negative 2. And if we, it doesn't look like we have 2, 4, negative 2 for any of these direction vectors. By the way, this is the direction vector for our line. But it does look like we have 1, negative 2, negative 1, or stuff like that. So instead, I'm going to use 1, 2, negative 1. So sometimes you just need to simplify things. You need to factor out something. How do you know what order to cross them in? It doesn't matter, because if you cross them in the other order, you'll just get negative 2, negative 4, 2, and those should still be proportional to one of these answers. All right, now this tangent line needs to go through the point 1, 0, 1, right? So let's see here. Some of these points don't even go through that. Like this one doesn't necessarily go through 1, 0, 1, especially, yeah, it doesn't because y is 2. This one does go through there, but they don't have the right proportions here. They have their y direction being 0. This one doesn't seem to go through there because we're missing a 1 here. All right, now it seems like the remaining 2 do go through there, but only this one, 1, 2, negative 1, is going to be proportional to the vector that we already have right here. Does f equal 1 and g equals 2 give us anything in this problem? No, not really. It just happens to be the values that you get if you plug 1, 0, 1 into these. Yeah, you don't really need to know what those are in order to solve this problem. But anyways, we end up with E here because we have the direction vector that matches 1, 2, negative 1, and we have the point that matches 1, 0, and 1 here. All right, let's go on to the next one here. Let f of xy equals ln of x cubed times y. Now, before I do anything with this, I'm immediately going to use log rules to write this as 3 ln of x plus ln of y. That will almost certainly make everything we're going to do here easier. All right, so let's see here. The directional derivative of f at 1, 1 in the direction 1, 1 is 4. Okay, well, that means we just need to do a directional derivative. Got time for that? Yeah, we do. All right. So we're doing the derivative in the direction of u at the point 1, 1. Okay, so this is going to be the gradient of our function dotted with u hat. Remember, it needs to be u hat. It needs to be a unit vector. All right, so let's see. What's our gradient? Well, the x part of our gradient will be 3 over x, and the y component will be 1 over y. Now, what's u hat going to be? Well, we have 1, 1 here. The magnitude of this vector is square root of 2. So I need to divide by that if I'm going to use u hat. All right, then I plug in 1 into here and 1 into there. And I have 3, 1 dotted with 1 over root 2, 1 over root 2. That gives me 4 over root 2. So that's going to be the value of my directional derivative. 4 over root 2 is not equal to 4. So that's going to be false. The function f does not change at 1, 1 in the direction -1, 3. All right, well, if it doesn't change in that direction, that means that it's going to have a directional derivative of 0. But another thing is that it's going to have a direction that is perpendicular to that of the gradient. So the gradient at this point is 3, 1, right? So is -1, 3 perpendicular to 3, 1? Yes, it is, right? So if I dot this with, well, technically it'd be -1/2, 3/2, or no, sorry, root 10. What am I doing? If I were to dot these right here, I have 3 and then, or sorry, -3 and then 3 root 10, that would give me 0. So our directional derivative is going to be 0, so there's going to be no change in that direction. How did it become 1 over root 2? I need to make sure this was a unit vector, and its magnitude was root 2. All right, so since I dotted this in this direction and I got 0 for my directional derivative, it's not going to change in that direction. We didn't even really need to divide by the magnitude here. It just needed to be perpendicular to the gradient right here. If you ever move in a direction that's perpendicular to the gradient, which -1, 3 was, then you're not going to change at all. How is it root 10? That's the magnitude of this vector. I technically wanted to do the directional derivative here. So I wanted to make this a u hat, but you didn't really need to do that because you would have gotten 0 anyways right here. The magnitude is 2. The magnitude of this one was 2. The magnitude of this is root 10. All right, so now let's look at this final question here. There is a unit vector u such that the directional derivative in that direction is 3. What do you guys think about that? Does that have to be true? Yeah, you can. Oh, yeah, you actually found a specific vector. Wow, I didn't even do that. Yeah, so yes, you can. It's because, so this is true. Reason being is, what's the magnitude of the gradient? Well, it's going to be the square root of 3 squared plus 1 squared, which is root 10. And last I checked, root 10 is greater than 3. So that means that our biggest rate of change is root 10, and also our greatest rate of decreasing is negative root 10. So you should be able to hit all of the rates of change in between from negative root 10 to root 10, meaning you're going to be able to hit 3 in there. Or you could have found that in the direction you had is 1, 0. Yeah, that was pretty clever. Yeah, so that specifically will give you a magnitude of 3. But it looks like Q and R are going to be correct here. Yeah. I don't think you're going to be asked something like that. It's could you just do this?
Yeah, it's not that overrated. It's kind of like a chunk, like just put the first part of it and then find the magnitude.
Yeah, you could do something like that. Don't worry about it. All right. We have one more here. I'd probably do one more, maybe even 2. Evaluate the limit. All right. Well, before I evaluate this limit, I'm going to simplify it. So I factor an x out of here. And I have y squared minus 4 over y minus 2. Oh, well, that's looking pretty nice, because this factors into y plus 2 times y minus 2, and we have y minus 2. down there. And then those cancel out here. And then now we could just plug in the vector, or sorry, the point 1, 2. So we're gonna have 1 times 2 plus 2, that will be 4. So this limit is going to equal 4 right here. All right. So yeah, there we go. That's all we had to do for this limit right here. All right. So be sure to fully simplify things. It made our life easier back here. I mean, we could have done some chain rule to do that, but let's be real. This is definitely a way easier thing to do the derivative of. And this is only possible by simplifying here. So when possible, try to simplify things because it really will make things easier most of the time. Oh yeah, and with that optimization problem earlier, simplifying it allowed us to use this method, whereas otherwise we would have had to use Lagrange multipliers, and who knows how hard that would have been. Well, so maybe some of you guys do if you tried it that way, but yeah, it may have been pretty tricky. All right. So let's see here. Consider the function.
Professor?
Yeah, what's up?
So I've actually got a question. So why is it called bonus questions 13 to 16? And if they are bonus questions, like, will we receive them for exam 2?
Well, they're bonus questions in that there are more than, like, how many points are available on here? There are, let's see, so it's graded out of 70, but then, oh, wait a minute, sorry, it's graded out of 80, but there are 90 points available. So it's a bonus in that sense. And our exams are like that as well. Because remember, there are a few extra points available, more so than 80. So the answer is yes.
Oh, okay. Thank you.
But they haven't changed it on campus.
Yeah, they'll probably do that at the end of the semester. Yeah. Yeah, because Canvas is really awkward with that kind of stuff. All right, anyways, let's try to squeeze in one more here. I think we can at least do that. Which of the following best describes the function f at the point 0, 0 right here? Okay, well, let's see here. In order to be one of these, we need to test if it's a critical point or not. So that requires us to find the gradient. All right, well, that's the x derivative of this. 2xy, oh, oops, not a comma, minus 3y plus y squared. Then the y derivative is x squared minus 3x plus 2xy. Okay, so there's our gradient. This is going to help us for all of these problems right here. So if I plug in the point 0, 0, does it make the gradient be 0? Well, since we have at least an x and a y in every single term, that means everything in here will be 0. So yes, we do get a critical point here. So we definitely know that's not true. We know it's a critical point at least. So now we need to do the second derivative test to tell us what type of point it's going to be. All right, so this was the x derivative. This was the y derivative, right? So let's do another x derivative. If I do another x derivative of this, I get 2y. If I do a y derivative of this, or equivalently, if I do an x derivative of this, what am I going to get? I'm going to get 2x minus 3 plus 2y. And then finally, if I do a y derivative of my original y derivative, I have 2x. All right, now remember, the key quantity for the second derivative test is this capital D, which is fxx times fyy minus fxy squared. All right, so in this case, we're going to have 4xy minus 2x minus 3 plus 2y squared. Now, if we plug 0, 0 into this, we get 0 there, and we get 9 here. So we get negative 9. So what happens if we have a negative D value? What does that tell us? It's going to be a saddle point or a Pringle. Yeah, that's right. It's going to be a saddle point. Okay. And it looks like we're out of time now. The other questions follow exactly the same method here. You just plug in these points into your second derivative test. Well, first you need to plug them into here to make sure they're a critical point, and then you plug them into the second derivative test here. All right, I'll actually do those problems 14, 15, and then also 16 here. And then I'll do the 2 free response questions tomorrow. So I will post that. And then on Friday, we'll be kind of having a free-for-all review where you guys can bring in your questions to ask.